Welcome to the third lab session of quantum topology 2 course. This is going to the last lab session, and this lab session is going to be one. So anyway, since unlike other courses, in this course nobody sent any questions to be solved in that session. So I have decided to go. Decided to do a family session, okay, where we will discuss all those concepts and techniques that we have learned from we have learned through the entire course. Okay, so so mm, so this course has started with compactness, right? So first let's list out all the topics that have been taught through the entire course. Yeah. So compactness, separation axioms, countability axiom, paracompactness, partition of unity, compactification, metrization. Okay. Then the main things are namely the manifolds, compact open topology, then embeddings. Yeah. So these are the main topics which we have learned throughout the entire course. Of course, in this live session, I personally could not attend all these topics because each topic contains a huge number of problems, and also we since in last 1 month we have solved the questions, the live questions of the assignments which has already been released, the answers. So for that we could not get full time to go through all these concepts, but we have covered the main concepts. Okay, so one second. Yeah, so so these are the main concepts. So first of all, let me go in the compactness. So what does mean compactness? So moral of the story is so basically definition of compactness is every open cover has a finite subcode. Okay, this is the basic thing of compactness, but of course this is not too helpful. Not too. For that there are many theorems. So for example, let me check those theorems first. Yeah, so some theorems are like that. Closed subspace of compact spaces are compact. So this type of theorem quite useful, namely compact subspace of an Hausdorff space is compact. Okay, remember here compactness is necessary. Okay, so Copenhagen. Now next the main one of the important theorem is the following, namely uh, yeah, if Y is compact Hausdorff space, X not does not belongs to Y, then there exists disjoint, there exists disjoint open sets U and V of X containing X naught and Y respectively. Okay, so this is what, and another theorem of chain compactness is that continuous image of compact sets. And there is one of the very important and useful theorem, namely suppose let f x to y bijective continuous if x compact and y Hausdorff, then f is homeomorphic. Okay, so this is one theorem. This is another type. This is true. And another theorem is known as the triple lemma. Of course, its statement are already known by everyone, so that's why I'm not going to. So since the theorem is known on proof 21, so I'm not going to the proof of this theorem. But the statement goes as follows: that suppose x and y, two spaces, and y compact. Okay. Suppose x and two spaces and y compact. Okay. So now, so this is x, this is y. Okay. Now let x not belongs to x. So let w be a compact set containing the slice x dot cross y. Okay. Then there is a neighborhood n of x such that x naught such that neighborhood n cross y contained in W. Okay. So this, sorry, the W is an open set. So this is the tubular. Okay, I'm not going to write the proof again here because it does not make any sense right now. So okay, so another property of checking the compactness is namely as follows: the finite intersection property. If I, okay. So what is this theory property here? First, a collection C. It's a not. It's a what? It's a collection of subsets of X. This collection is said to have finite intersection property if for every finite subcollection C1, C2, Cn of C. The intersection C1 dot intersection Cn is not okay. So this is what we mean by finite intersection property. In short, it is FI. Okay. Now, so after FFP, there is a theorem which tells that. So after with this theorem, which tells that um, if X is in space, okay, then X is compact if and only if every collection C of closed sets in X having FIP, the intersection C belongs to C, all elements is non-empty. Okay, so yeah, so this is one thing we should remember. So okay, so using this thing, so there are some, of course, some great nice exercises. We have already seen those exercises in first or second of this course, but anyway, so I think it's better to list out the exercises one again. So the first question is as follows: that any compact space is not. Means what? If we take any two closed disjoint sets A, B, then there is an open set U and V disjoint, so the intersection is empty. A and B both are closed. Okay. So this is one very much compact normal. Okay. And another second property is as follows. Sorry. Another second property is as follows that yeah, if if x to y continuous and x compact, y house, then f is a closed map. Okay. So this is one thing which is quite important today. And also do note one thing that this second question depend on the first question. Okay. So yeah. And also, yeah. So there is one theorem which is known as the generalized tube lemma. Well, honestly, I don't know whether this generalized. Okay, yeah. Honestly, I know that this has been done in the in class actually, but possibly problems had not been solved for this generalized tubulema. Well, you can find out in or you can email me. I will tell you the source from which the tubulema related, I mean, problem related to the generalized tubulema you can found. Okay. So first, okay. So first, let me tell the statement first. Once again, let A and B be subspecies of X and Y respectively. Let N be an open set X cross Y containing A cross B. Now the statement is that if A, B are compact, then there exist open sets U and V in X and Y respectively such that A cross B sub of U cross B sub of N. Okay. So this is the statement. Okay. So first one thing, let me search one minute, one two minutes. Is there any interesting problems or can be found out or not? Let me search. Kindly wait for 1 2 minutes. Once. So Yeah. So these are some open cells which you are getting. Okay. I mean, so these are sorry, this is the generalized tubular. And also, uh, one more thing. Also, there is one. Okay, so there is also one theorem which possibly we could not get. By the way, so sorry, I could not found any good questions or generalized tubular that can be done short time. So anyway, if you want to solve the problems for generalized theorem, please drop an email to me. I will reply. Okay. So yeah, so there is one theorem. I think this theorem has not been done in NPTEL actual class, or also it has been solved in live session also. So this theorem is not too much important, but this theorem is something which one can't ignore. Okay. So the theorem is goes as follows: that let X be uh, non-empty compact Hausdorff space. Now, if X has no isolated points, then X is uncountable. Okay, so this is the theorem. Okay, so for example, this implies what? Close 0, 1, uncountable, real line. Those are just some things. Which is not ignorable. That's all. Okay, so let me research one thing that let me search the questions. Okay, so question isn't here actually. Yeah. So, so due to this theorem, close 0 1 and also open 0 1 real, and these are all not open. So these are some quite interesting fact I think we should not ignore. Moreover, okay, so now coming to the local compactness. So in local compact we have one important concept, namely 1 point compact. I mean, first concept is compactification, and probably one one point. Okay. So 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 this is, and of course I am not going to tell the definitions of this thing again. But the important fact is that, so what does it want to compactification is the space can be made compact by adding only 1 point, right? Now the point is that if X is locally compact first of there, so I mean by adding 1 point. Now question is, suppose we have real. I mean, so that is X infinity. Now problem is X infinity is by definition can be made by John Union, but think how we actually can get this thing correct. So for that, what you can do? So X infinity, X in third order. Let's take one compare. So so for example, suppose we have a real line R. Now what is one compared to real compact? So what we will do? Real and infinite thing, right? We can make it as like open zero finite interval, and we can put this push together. So this thing are looking like this. Okay, now just we add on point, so this thing is nothing but s1. So in this we can do compactation. What is the map will be r to s1 will be map, so if you got f, so the f is an homeomorphism onto its image. Moreover, So our question is onto simulator. So S1 minus the image of f consists of single point. So in this type of thing will happen, then it's a wonderful configuration. Okay, so anyway, it's not that it is not directly always possible to find one configuration, but it shows that some kind of existence. Okay? So anyway, so that's all for the compactness portion. Now let's go with the separation and countable reduction. One second. Um, one second. So I couldn't find some good questions right now. Only wait. So yeah, right. Hmm. So, okay, so in separation axioms and counter axioms, so the counter axiom it comes with two things. One is first countable space, another is second countable space. Okay. Now, note two things. So, first countable space is means every point has a countable collection of neighborhood systems, and second countable space it has a countable basis for the given topology. Okay, this is what it. Now, so now of course, second countable plus first countable, and this type of inequality you need to keep in mind, but converse is not. And there are some examples which we have already seen while taking the session. Okay, right now I'm going to not going to do the same group again and again because it really doesn't make any sense. So this is one thing. And second thing is separation axiom. So in separation axioms, we have some many things, namely P0 space, P1 space, T2 or house dot space, T3 space that is T1 plus regular, T4 space T1 plus normal. So these are some things which we always need to keep in mind. So and regular means if we take any point, if we take any closed set and x doesn't belong to this, then there is an open set U and open set V is the university to be empty. And normal means if you take any closed set, suppose A, B are disjoint closed set, then there exists an open sets U containing A, P containing B, such that U intersection V is equal to empty. Okay, so this is normality. Okay, and moreover, okay, when you wait for So, yeah. So these are some, and of course there are some concepts as T 4 by 2 and T square. But anyway, we are not going to bother about this. Okay. And first of all, it's it's everything is implied by others in the reverse direction. That is T4 is a proper subset of T3, is a proper subset of T2, is a proper subset of T1, proper subset of T0. Okay. And anyway, so the properness can be shown by checking some counter examples which we have already seen while the live sessions. So anyway, we're not going to check those. Okay. So there are quite important, quite interesting question. Of course, you should keep remember in mind. Suppose if G is a map from X to Y, it continuous, and plus if X is Y Hausdorff, then show that X says that if X is equal to Gx, it's closed, right? So this is one thing you should always keep in mind. Okay. So this is one thing. And anyway, this question can solve many ways. But I have solved this question 3 times, so I'm not going to solve this question. And also one more thing is that continuous image of, I mean, this is one disadvantage of regular normality, that continuous image of, sorry, continuous image of normal or regular space may not be normal or regular. Okay. So this is one disadvantage of regularity, but anyway, we are not going to bother about this. We have seen some examples. That's all. Okay. But when it will happen, so unnecessary condition. let Px to y be closed. And surjective map says that y is constant for all values. And this is called a, and this type of map so means the perfect. Okay. Now, okay, kindly wait. Okay, wait, kindly there is a internet issue. Okay, so this type of maps is not the perfect. Okay. Now, the thing is that if x to y is the perfect map, and if x normal or regular, this implies y will be normal or regular respectively. Okay, this is quite extremely important thing. And moreover, and like local compactness. If let's say local compactness is perfect map, then it will be local compactness. Okay. So this type of thing we need always to remember. Okay. One second. Okay. Okay. So this is one thing I think we need to discuss this. And the second thing is that namely there's one important fact is regular plus countable basis is normal. It's quite important thing which is already remember. And moreover, once again, Whoa. So, and one more thing is that every compact household space is normal. So this is the thing which we have already discussed initially. Okay. And there is one more thing is that paranormal is not normal. That is S omega cross X closer is not normal. So product of normal space may not be normal. Okay, so this is that's all for the normal. Okay, so we are running out of time now. So hope all the best for your exam. I hope you all do a very good job in while writing the exam. Okay, I hope to see you in some next course. So so that's all for today. Please go through the concepts properly once again, and if you have any doubts, please ask me. So I will definitely. Okay, thank you very much for at this live session. I look forward to what you said very very much. And as I said earlier, if you have any doubt, please drop an email.